Hi, this is Mike Lawless, and in this video, I'll discuss various aspects of ADMET Predictor models. This is simply an outline of the presentation. I'll start off discussing the model editor, then move on to predictions that are out of scope, then discuss descriptor sensitivity analysis, structure sensitivity analysis, confidence analysis or estimates that are included with our classification models, and then finally, regression uncertainty. We'll first start out discussing the model editor. And this is under Tools, Model Editor. And we'll bring up this dialog box and I'll just make full screen. In the model editor, this defines all the models in ADMET Predictor. And the first column just lists the name of the model. So this is the model name that will appear in the ADMET Predictor spreadsheet. And then you can turn off or on various models. So if there's any models that you don't want predicted, say permeability for the cornea or skin permeability, you can just turn them off here. And then when you calculate properties, you will not see those. Each model has a model type. So if we look at the first one, PLS, this means that there's a PLS file in the data local directory that defines this model. So this is just the diffusion coefficient. M log P is just an equation encoded as a PLS file. Then you can take a look at that PLS file. The S plus log P model is an artificial neural network ensemble regression model. Then we get some specialty models or model types like log D, pH. Most of the models you look at will be either regression or classification A&E models, such as this blood-brain barrier filter model here. Then each of the models has a file that backs it up. So for this PLS file, there's simply one going to be called s underscore diff underscore 2D dot PLS. And that points to that file. Now, down below, I have some user-defined models, and these are simply net files. So there's a base one underscore PIC50.net file that gets written to the app data local directory when you export a model from ADMET Modeler. The next field here can be 3D if you have a 3D model for the endpoint. The determining descriptor determines how the calculation is going to run. So if, for example, if the log D model is dependent upon the log P model being evaluated, and for some reason this was turned off or wasn't computed, then it wouldn't calculate the log P model. Now, if we go down a little bit further and look at some of our SIP substrate models. So this depends upon the number of SIP sites in S plus log P. For the number of SIP sites, if that's equal to 0, output of the model will be no site. Any compound that doesn't have the descriptor M and SIP sites equal to 0, if it's equal to 0, it doesn't have any sites and therefore it doesn't evaluate the model. It just puts out no sites for that. The auxiliary factor is typically what can be multiplied by the model and the output. So for example, if we look at our S plus SW model, it's molecular weight. So the output of the model gets multiplied by molecular weight. And the reason this is done is because the model was developed in molar units, and multiplying by molecular weight will convert it to milligrams per milliliter in the output file there. Then if we go on to the transform, this can be anti-log, none, or anti-log it. So another, getting back to the S plus SW example, this is set to anti-log. So the model was built in log space. So if you take an arbitrary compound and you evaluate it in the model, it will first calculate the log of the solubility in molar units. Then it will take the anti-log of that and then finally multiply that by the molecular weight. We also have a couple columns for the minimum and maximum value, and these are set for some of the models and not for others. So for example, if we look at S plus PEF, S plus PEF, the maximum value is 12. So even if the model evaluates it at 13, what's going to be displayed in the cell in ADMET Predictor is 12. And then some of these also have 0. So for example, aqueous water solubility or pH saturated only goes from 0 to 14. For RBP, we've got lower bound of 0.55. And then for fraction unbound to microsomes, we've got 0.011 in there. And then the tooltips are what you see when you hover your mouse over the column title. So let's go ahead and close that, and then we just can look at a simple model, ADMET risk. So if we cursor over that, you'll see the tooltip associated with it. Okay, now let's look at an image of the applicability domain for the model. So every model has what we call an applicability domain, and it's based on the minimum and maximum value of each one of the descriptors in the data set. So in this example, we're looking at a very simple model with descriptor 1 and descriptor 2, and we're looking at only the training set molecules. And for each one of the descriptor values, we know what the minimum and maximum value is for each one of the molecules in the training pool. We then add a 10% border around that. So we give it a little bit of leeway. And then when you predict an arbitrary molecule, if all of its values are within the minimum and maximum value of the applicability domain of the training set, then we would highlight, or those are said to be in-scope predictions. So they're inside the minimum and maximum value for each one of the descriptors. If any one of those values is outside the minimum or maximum border, then we would color that in magenta in the interface and underline it, and it's said to be an out of scope prediction. Now we'll look at some values for, or some predictions for the aqueous water solubility model, and specifically we'll look for out of scope predictions. For every model, there will be a corresponding or OUT attribute. So these attributes you're seeing here are associated with are labels for any predictions that are out of scope. Now, if all of the predictions for this data set were in scope for this Andro filter, then the column wouldn't appear. So if you're looking for the out of scope column and it doesn't appear, that means all the molecules in there are in scope. If we scroll down here to the S plus SW column, we'll click OK, and it will add it to the spreadsheet or insert it. We can sort in descending order, and then you'll see where all these ones are, indicating that the prediction for S plus SW is out of scope. Now let's look at an out of scope prediction for S plus log P and try and figure out which one of the descriptors is out of scope for it. So I'm just going to set the contents here to the S plus log P model, and then also set the out of scope here contribution or value for the S plus log P model also. Okay, and I'll undisplay this column. Now let's find a particular example here, 8071, which is out of scope. So I'll hide everything except for this particular model here. And we can go into what's called descriptor sensitivity analysis. So I'll click on the DSA button, and we'll only do it for this particular row. And we'll bring up the S plus log P prediction. So the prediction here is 2.4 for the log P. And if we sort these in order, the input, or this has a list of all the descriptor values, and any of them that start with 2 asterisks are out of scope for this model. So in this case, this is the SAAAN, and that's an E-state indice for aromatic nitrogen, and then an aromatic atom, so N-fused rings. And we can go to the sensitivity line, and this shows us the model minimum and model maximum for this particular descriptor. So these are the values, the minimum and maximum values for this particular descriptor in the uh, in the training set for the S plus log P model. And you see the value for this particular molecule is up here around 3.9, where the model maximum is more like 2.3. What we're doing here with the sensitivity analysis is we're taking each one of the descriptors in the model and we're varying it uh, around its value. So for TPSA, which is one of the descriptors in the log P model, the value for this particular compound is right here. If we lower the TPSA, holding all the other descriptors fixed, the log P value goes up. If we increase it, the log P value goes down according to this red line. Now, the larger this slope, in other words, if you change this a little and it changes the S plus log P drastically, that is a more sensitive descriptor. In other words, the model is highly dependent upon that particular descriptor. In the case of this one that's out of scope, if we vary the values, it could vary between 4 and say a little bit 2.4 here. So that's not as high a variation as if we vary one of the TPSA, which would go from 4 to -1 for this particular model here. We can also sort the sensitivities. So this is the default. And if we look at molecular weight, now here molecular weight has a positive sensitivity because if you increase the molecular weight, you increase the S plus log P. And you can kind of analyze these descriptors and try and figure out which descriptor needs to be changed in order to change the output. And then you try and change the molecule in order to change that descriptor and therefore change the log P or modify or optimize the log P of the particular molecule. I just want to go back and mention that for this compound that was out of scope, you see the model maximum is around this value, and it would have given a log P of around 3. What the program's doing is extrapolating this distance and giving it a value of 2.4. And this sensitivity is only 0.04. It does contribute a little bit to the model, but it's not as high as some of the other ones like TPSA. So I would say that this prediction, even though it's got one of the descriptors out of scope, that is still a pretty solid prediction for this molecule. Now let's switch gears a little bit and talk about structure sensitivity analysis, or SSA analysis. This is a way to relate the structure or the atoms in the molecule to the prediction, and it kind of complements the descriptor sensitivity analysis. So if we take this molecule, so we've highlighted, it's a fairly simple molecule. It has a predicted log P of 3.5. And we highlight it and then we click on this button here, which is the SSA analysis, and we select a model. Now, there's only certain models that we've created the structure sensitivity analysis for, and we'd like feedback if you'd like additional molecules or models added to this. So when you select the model, it takes the compound and it highlights it either red, green, or kind of a gray in between color here. And then the legend is for S plus log P. If the atom lowers the log P, it's going to be colored red. If it raises the log P, it's going to be colored green. So we see that this nitrogen here is 1 in the red, so it's responsible for a lower log P. It's obviously a polar atom. And then these two carbon atoms on this fused ring are green, so they're responsible for increasing the log P of the compound. So let's just double click on this compound, take it into MedChem Designer, and make a couple copies of it here. Now, For this particular molecule, I'm going to change this nitrogen, which typically lowers the log P, and I'm going to change it to a carbon. This carbon here uh, increases the log P. So if I change it to a nitrogen, I can hopefully lower the log P. And then I'll just click ADM, the ADMET button. And then if we look at the log P, this is the original compound with the log P of 3.5. Now I've changed the nitrogen to a carbon, and that nitrogen lowered the log P. So when I change it to a carbon, it raises the log P to 5.048. Then when I changed this carbon, which was highlighted in red, or excuse me, green, indicating that it increased the log P, then I change it and it changes to 2.56. So it's a lower value by 1 log unit. In this next section, I'll discuss confidence estimates for classification models. So here's a typical classification model, CYP1A2 substrate, non-substrate model. So it predicts whether a compound can be a substrate or a non-substrate for CYP1A2. And you'll notice each entry has a yes and then a number in parentheses, which is the confidence estimate that we have in that particular prediction. You can add these as a separate column. So I'm going to insert a column here. And these are listed under the CONF. So for each of the classification models, there'll be a CONF, which will separate this out as a separate column here. And then we can go ahead and make a plot of this as a distribution plot right here. So this is the confidence estimates here, and they range from empty. So if the prediction is out of scope, we don't supply the confidence estimate, and then it varies down to about 48, 46 for the low estimate, and then on the high end, the confidence goes up to 97%. And generally what we say is that for a classification model, if the confidence estimate is below 60%, then the model really is uncertain about whether it's a yes or no. So we usually recommend that you get an experimental verification of that particular endpoint. So let's look how these confidence estimates are created. They're created when you build the model. So any classification model you created, when you take a look at the P&O file or the predicted versus observed file, you can click on confidence estimates. And then the first type graph we're going to look at is the predicted prediction and error distribution. So this black line are the number of predictions at a certain number of positive vote counts. Remember that all our models are ensembles of 33 artificial neural networks. If all of them vote negative, in other words, there's no positive votes, you would go up to this axis here. This is on a log scale, but there are about 390 predictions that have 0 positive votes. And then the red line is how many of those were incorrect predictions. So in this case, about 8 of those 390 were incorrect votes. And then you can go across for each one of the number of positive votes. And so on this end, where mostly all ensembles are predicting a negative, you would expect fairly good predictions. On the other hand, where you predict everything as positive, you get, again, pretty good predictions. Kind of in between there, where these black and red lines come together, are when you're going to get the most uncertain predictions here. So for example, at 18 positive votes, there were 11 predictions that had 11 positive votes, or excuse me, 11 positive votes, and 8 of those were incorrect. So this is where you'd see the highest uncertainty. And then you click on the error rate, and now it shows in red kind of the difference between those two lines. And then this is our approximation of this red line. And remember, this dashed line has to incorporate all the highs and lows. So it kind of cuts through the middle here. And then also does it for the positive. This is what's called a split binomial, where we approximate the negatives with one curve, the positives with another curve. So then when you predict an arbitrary molecule, you determine how many positive votes it has. let's say it has 20, and then you would go up to the black line, and so the uncertainty would be uh, about zero point 0.5. Now, this is for the previous version of the SIP1A2 model. We rebuilt that in ADMET Predictor X.3. In the last section of this tutorial, I'm going to talk about regression uncertainty. So here I have two molecules, and I've displayed the predicted aqueous water solubility. In order to turn on the display of regression uncertainty, I'm going to click on the settings button here and then go into display and turn on display uncertainty estimates in the spreadsheet. So when I click that, it puts two numbers in parentheses for each regression model. So these will be displayed for all the regression models, whether it's in scope or out of scope. And the first value in parentheses is basically the lower bound on the regression uncertainty, and the other value is the upper bound on the regression uncertainty. Now, since this model was built in log space, this is a log normal distribution. And again, the values are obtained by analyzing the variance in the individual neural networks that make up this prediction. So I'm calling this the average, or this would be the output of the ANNE model. So this would be an average of all the neural networks. And then we do a regression uncertainty analysis to get the upper and lower bounds. And I'm going to illustrate how you can use these upper and lower bounds to kind of investigate whether that prediction needs to be more accurately measured, maybe in the lab, or if the estimate, the prediction is good enough and it's not going to affect the results. So the way I'm going to do this is use the HTPK module. So I'm going to highlight this particular compound and then create a CP time curve. So clicking on the CP time curve, and when you bring up the HTPK module, if we go to the advanced menu, this button here will fill in the values for the aqueous water solubility. So it uses all the mean values. So for this compound, it's very low solubility, 3.8 times 10 to the minus 6. And we're going to go ahead and run that prediction. We get a low fraction absorbed of 1% for this molecule. So low fraction absorbed. Let's say we take the upper value in the CP time curve. So again, I'll click on CP time curve, and I'm going to display this new curve on top or in the same graph as the new one. Now I go into the advanced tabs, and let's change this to the upper bound 4.686 e to the minus 5. Click OK, and then run the simulation here. Now, the first simulation is in blue, and then the second simulation is in red. And this increased the fraction absorbed to 1.93. The previous was 1. So this is not very sensitive to the solubility prediction or the range. We're predicting a very low solubility, and it's so low that even the high value doesn't change the fraction absorbed a whole lot. So if you're confident in that prediction, changing it to the upper bound is not going to change things very much. Now let's take a look at a compound that has a higher predicted aqueous water solubility. Again, we're going to highlight that compound and create a CP time curve. This time we're going to do a 100 milligram dose. Typically for low soluble compounds, the higher the dose, the lower the fraction absorbed for the compound. So we'll just go ahead and run this, and we get a CP time curve, and the fraction absorbed is about 30%. Now let's go back in here and raise the aqueous water solubility to the upper bound on the prediction here. So it's 3.016 e to the minus 2. We'll go ahead and save that. We'll display it in the same plot here. Click OK, and then run. So the first prediction here had a fraction absorbed of 30%. And then if we go to the other one, now it has a fraction absorbed prediction of 91%. So using the upper bound really changed it. And so you're seeing that this compound is very sensitive to the oral bioavailability prediction. What we're doing when we change these values is kind of doing a sensitivity analysis of that prediction and using the upper and lower bounds to determine how sensitive the fraction absorbed is to this aqueous water solubility prediction. So for this compound, it's right in the range where it's going to change quite a bit. We could also simply do a parameter sensitivity analysis of this. So we'll do 100 milligram, go ahead and run that. Now, if you look at the blue curve, which is the solubility, this is the median value, and then we go down to lower values, and you can see how it really does change the fraction absorbed. So this compound, at least with our predicted aqueous water solubility, the fraction absorbed is very sensitive to that. So it'd be nice to get a better, maybe an experimental value on that, and then use that in the simulation. So that's it for this video. I hope you've enjoyed it and learned something. Thanks for watching. If you have any questions, please feel free to send me an email, and we'll see you next time. Bye-bye.